Okay, welcome to problem number 2 of proving the Pythagorean theorem. We're going to use algebraic reasoning this time instead of a theorem that we've necessarily just learned. I think this is a little bit easier to see because it's a very visual proof and it's a lot more geometric, I think, than the last proof was. So it says use the diagram shown and the following questions to prove the Pythagorean theorem. So we're going to use that diagram there. The questions are going to guide us through this proof. So this is kind of like an outline of your proof. It's not an actual proof, but it's more of an outline if we were to set this up to solve as a proof. Okay, so it says number 1, what is the area of the larger square? So there's two different squares in our drawing here. I'm going to kind of highlight one of them. Now, the area of a square is listed as area equals s squared, in other words, side squared, or area is equal to length times width, since technically a square is a rectangle. Now, what is one of the sides? So if I'm wondering what one of the sides is, I have to represent it as a plus b. And since all sides of a square are the same, every single side is a plus b. So I'm going to do a little bit of algebra work here to the right. And if you could just copy it down and follow along. So we really have area is equal to a plus b, one side, times a plus b, which is the other side. So this is area of the large square. Now, when we multiply a binomial times a binomial, we have to do a thing called double distribute. Okay? Let me remind you, distributing. So if I had an equation that looked like this, 2 times x plus 5. I could distribute the 2 to get 2x plus 10. Well, the difference between that and what we're doing is that what we're doing involves a binomial times a binomial, not a monomial times a binomial. So a little bit different here. We have to do a thing called a double distribute. In other words, a times a and a times b. So a times a is a squared. A times b would be ab. Now the other part we have here is we have the second b, which has to multiply a. So that's a times b again. And then we have the second b, which has to multiply that last b. So b squared. Okay. So basically every term needs to be multiplied by every other term. And since there's two terms, we're going to double distribute. Okay. From there, we can do a little bit of work and simplifying it. One of the things that you're going to notice is that I have AB and AB, which can be combined into a squared plus 2ab's plus b squared. Okay, that's about as simple as we can get. We can't combine anything further from there. So question 1, that is your answer. Okay, a little bit of work with distributing. You might have heard of this term called FOIL, first, outer, inner, last. That's the same thing as double distribute. We've kind of gone away from that saying. We're just going to call it double distribute. Okay? All right, so moving on to question number 2, it says, what is the total area of the 4 right triangles? Okay, so I'm going to erase this here so that we can see what we're talking about. We have 4 right triangles. So here's one, here's another, here's a third, and here's a fourth. You notice that all 4 of those triangles are congruent. How can I tell? They both have sides of AB with a right angle in between them. So by side angle side, all 4 of those triangles are congruent. So I really have 4 of those. So the area, and I'll put a little note down here that this is area of the triangle, is equal to 1/2 base times height, right? Since it's a right triangle. But here's the other thing, is I have 4 of them. So I have 4 times that. Okay? So area is equal to 4 times 1/2 times your base. In our problem, our base is going to be a or b, doesn't really matter. So a times your height, which ends up being b. Now when I simplify this a little bit, 4 times 1/2 is 2ab. Okay? So a little bit of algebra work gets us to 2ab. Third question says, what is the area of the smaller square? Looking back at our drawing, I'm just going to clear the ink here so we can see everything. In our drawing, this is the smaller square. And remember before that I said that area of a square is just side squared. If my side is c, area is equal to c squared. other words, length times width, c times c would be c squared. Question 4 says, what is the relationship between the area of the 4 right triangles, the area of the smaller square, and the area of the larger square? Okay, so let's look back at our picture up here. It says, what is the relationship between the area of the 4 right triangles, the smaller square, and the larger square? You should see that the 4 right triangles, if I can highlight this here, highlighter, let's move this over and let's use yellow. In other words, the 4 right triangles, the area of those, that's why I'm shading these in, the area of the 4 right triangles, the area of the small square, so shading that in, I happen to choose green and gold, go pack, and the area of the large square. Now the area of the large square, I'm just going to highlight the outside. The large square is all of it together. So the relationship is the area of the small square plus the area of the 4 right triangles is equal to the area of the large square. Okay, so I'm going to scroll down here. Oop, got to get off of that. So the area of the 4 right triangles plus the area of the small square must equal the area of the largest square. So what we set up here is this first part here is the area of the large square. It is equal to the area of the 4 right triangles plus the area of the small square. To simplify this, to get to a squared plus b squared equals c squared, you'll notice that I have 2ab on the left side and on the right side. So they're going to cancel off after I subtract them out, and I get a squared plus b squared equals c squared. And thus, you've proved the Pythagorean theorem again. Okay. All right, so grab the worksheet that I have as a handout, and that is your homework. It is following this along, doing this with just 2 other pictures that are similar to this.